Yeah,
Right.
the typing feedback was a little slow. Or
Okay, you guys ready?
delay, not feedback.
Elijah is sliding down a water slide that is 3 meters long, and the angle of this is 26 degrees. Theta equals 26 degrees, and there's a coefficient of kinetic friction that is 0.26. Do you remember what that coefficient of friction is?
Mu2
Yeah, it's your mu.
or mu.
And the question is, how long does it take for you to splash into the pool? Here's the pool. I think we have all the information. I'm going to go through this pretty quickly. I don't need to go through each page, each step. This is almost a warm-up. You ready?
Yeah.
I'm going to start off with a free body diagram. A free body diagram points out the forces. What forces do you see on this person? You.
Biggest one is normal force, which is going parallel to the slide.
Nope, perpendicular to the slide, but I get what you're saying.
Perpendicular, sorry.
Is it right if I, instead of, I've been saving that as N, is it right if I write that as Fn for now?
Yeah.
Force normal?
Yeah, that's fine.
The reason being is because when I use the units, I abbreviate newtons as N, and I don't want to confuse myself.
Oh, okay. That makes sense.
Okay, what else do you see?
The friction force.
The friction force.
Which is going... Yeah.
Which is going exactly...
Which is going, I suppose...
parallel to the slide.
Yeah. Right.
I'm going to call that FF. In fact, I'm going to call it FFK. That is the force of friction kinetic.
Right. It's not static because I'm moving.
Right. If it were static, you wouldn't be moving. All right. Anything else?
I forgot what W stood for. Weight. Weight.
It's the weight, which is equal to mass times gravity. Are we cool? Now what we're going to do here is we're going to slant the coordinate system, which means that the W is actually the one that is off kilter. These two are actually exactly on the X and Y direction.
Yep.
And I don't need to make that same geometry argument that with you again, but this is theta over here. Making this WY and this WX. And WY is equal to W cosine theta, and this is W sine theta. Cool?
Yep.
All right. Add up all the forces in the x direction, and that's equal to mass times acceleration in the x direction. And here's my first question to you. Is acceleration in the x direction 0?
No.
No.
Wait.
No, it's not. Okay. It's not 0. Because you're accelerating down the ramp, right? So what forces do you see in the x direction?
Right.
They're all over here.
Oh, right. Sorry. There's F of K or FFK.
Yeah, force of friction kinetic. So FFK.
Yeah.
Is that positive or negative?
Negative.
Good.
Because it's going against where we're heading.
Right. Positive x is that way. Okay. What else?
I don't see any others. Oh, right. The WX or W sine theta.
W
which is
sine
positive.
theta, which is positive, is equal to mass times acceleration in the x direction. All right. Here's the problem that I'm seeing is I wasn't told the weight of you. I wasn't even told your mass. This could be a problem. But anyway, let's figure something out. All right. Your FFK, that's equal to your mu force, or your mu number times the force normal. Okay?
Right.
So I can figure out what the acceleration is. All I got to do is divide everything by m. Are we cool? The problem here is I don't know what Fn is. What is my normal force? Because I can't just solve this thing. I don't know what Fn is to begin with. So what I'm going to do is, let's try turning to the y direction. If we got as far as we could on the x direction, let's try going in the y direction. Maybe it might help. So my sum of the forces in the y direction is equal to mass times acceleration in the y direction. Now in the y direction, is there an acceleration?
Yes, because you're moving down, technically.
No, because you're not moving up and down off the ramp. The y direction is going this way. And you're only moving this way. Do you get it? Look at this.
Okay. Yeah. Yeah.
You're only moving in the x direction down the ramp. Your sister got this. Remember, she was telling you, no, you're not flying off the ramp.
Oh, that's right. Sorry.
If you were flying up off the ramp or diving into the ramp for some, I have no idea why, then you would have an acceleration in the y direction. But you're only going, we set up the coordinate system so that all of your direction is moving only in the x direction, and there is no y direction motion here. So your acceleration in the y direction is equal to 0. We cool? All right, what forces do we see in the y direction?
Normal force.
Okay, Fn. Positive or negative?
Positive.
Good.
And then there's W cosine theta, which is a negative.
W cosine theta, which is equal to 0. Oh, and you're right, that is negative. So, hey, can I figure out what Fn is? Sure.
Yep.
Fn is equal to W cosine theta. We're cool with that?
Yep.
So that means I could take this thing over here and plug in what Fn is equal to. So negative mu times W cosine theta plus W sine theta is equal to MAX. Actually, I'm not even going to put a subscript on that A. I'm just going to change it from AX to A.
Yeah.
Because there's only one acceleration. There's no point in having an AX if there's no AY.
Right.
Okay. W is the same as mg, right?
Yep.
All right, so this is negative mu mg cosine theta plus mg sine theta is equal to ma. Check this out. You ready?
Mm-hmm. Alright, sweet.
So A is equal to g times sine of theta minus mu cosine theta. You're right, there's a mass in every single one of these terms, so I divided it by mass.
Sweet.
Okay.
Makes it easier.
Let's talk about this thing, all right? Shall we? Let me think. Does it make sense that your mass doesn't matter?
Yeah.
Does it? So, like, let's put you on a little boogie board, and you're sliding down this ramp, okay? And then what we do is we say, all right, well, here's what we're going to do. You slide down the ramp, and you make it down to the bottom at a certain amount of time, okay?
Okay.
Now, let's put your entire family on that boogie board.
Okay.
Will you make it down in the same amount of time or slower or faster? By putting your entire
I
family
would
on the...
say.
Okay, what would you say?
I would say. I'd say faster.
Yeah?
We'd have less friction, I suppose, because we weigh more.
Okay, by putting your entire family on the boogie board rather than just yourself, what did I change about it?
Our weight.
The weight, or the mass of the person, the mass of the object that's on the board, right? Now,
right.
The mass of the object would... A greater mass on the object would cause more friction, right? Because the bigger the mass of the object, that means the bigger Fn cosine theta is. Or W cosine theta is.
Right.
That means your normal force is big. And if your normal force is big, then mu times that normal force is even bigger, right?
Right.
But on the other hand, so I would say going slower, right?
Right.
But on the other hand, a much more massive object has more inertia, so it's harder to stop. So I would say going faster.
So is it like on Wednesday when you taught us about static motion, after it makes that initial push, it kind of moves better?
We're assuming you're moving in this case, yeah. But what I'm saying here is force of friction increases, so you're going slower. But inertia increases, so it's harder to stop you, so you're going faster. And we've seen right here that the mass doesn't matter. So mathematically, you can say, well, sure, you're going the same speed, actually, because in this equation right here, where is mass?
Not there.
It doesn't matter what mass is. It just matters what g is and theta is and mu. That's it. And in both situations, you had the same g, theta, and mu. You just had more people on the boogie board. But that didn't matter. And what I went through with you is we said, okay, the math is telling us one thing. Does that even make sense? You know what I mean? That's my favorite thing about physics, is the math tells me one thing, but does that even make sense? Is that true? And I think to myself, and I think, well, if it's a greater mass, then there's more friction, so it slows it down. But if there's a greater mass, then there's more inertia, so it's harder to slow down. So maybe those two effects cancel each other out. Damn, physics just taught me something about the real world. Isn't that kind of cool?
Huh.
All right, we didn't actually solve the problem.
It's changing my sense of common sense.
Yes, that is a great observation. Physics changes your sense of common sense. A lot of times it agrees with your common sense, and a lot of times it disagrees with your common sense. But I hate to say it, when it disagrees with your common sense, it's because your common sense is wrong. And that's pretty crazy.
Yeah.
I warn you, we didn't actually solve the problem. I asked you for how long it takes to get to the bottom. But think about this. If I knew the initial velocity, which is 0, and I know the distance, which is 3 meters, and I know the acceleration, which is whatever that chunk is, and I know the time, then the only thing that I don't care about is V final. There's an equation that I can use to help me figure out this answer. And all you got to do is solve for time. So you take this thing over here, plug it into here. You take that and have it as a d. This thing cancels out, and then you solve for t. T is the square root of, t is the square root of 2 times 3 divided by a. There you get your answer. So, this thing brought us all the way up to where we need to go, and then we had to refer back to, hey, remember those old school equations, especially your good old friend Pervner that you have grown to love so much? They're still important. They still come into play. We cool? But I love that. That's my favorite thing about physics. It blows my mind to think that what's happening is physics is teaching me something that I didn't really know. I just think that's exciting. All right. Let's do this one. I'm going to erase this, if that's all right with you.
Okay.
Okay.
Yep, I have it all written down.
All right. Elijah is working at a moving company. And you know they have those trucks that have a flat bed? You know what I'm saying? They have trucks that have a flat bed. And there's a piano on that truck that has a flat bed, and it doesn't have wheels on it. It's just sitting on there. And what the guy is doing is he's starting to raise the thing so the piano is sitting right there. And Elijah's not here. He's the mover. He has to catch this piano. Elijah, looks like you're gonna die. But I'm just saying. All right.
Yeah.
Now, the coefficient of static friction is behind this page, and I can't even see it. Okay, wait. Oh, okay. So, what you guys are doing is you guys are doing this. You're saying, we noticed that when I move this angle theta to be, let's make it 27 degrees. I'm not even going to put in 27 degrees as a number because to me numbers aren't really that important. It's the physics of it. But you say, I noticed when I move this thing to 27 degrees, this thing doesn't move. But when I move it to 28 degrees, that piano starts to slide down and it can almost kill me.
Oof.
In fact, I'm looking at this problem that I got from the book, and I'm not going to solve it. I'd rather do something else. You want to know why?
Because we did this on Wednesday?
Yes, exactly. I was going to say, the question was, what is the coefficient of friction between there? And we already know. The coefficient of friction, static, is equal to tangent of theta.
It's 10. Yep.
Yeah. So I'm not going to solve that one. That one was... We did that one already. It's just a different story, but it's really the same problem. Do you notice that in physics, when I give you these general ideas of how to do something, I really can't change it up on you very much, can I?
Yeah.
Okay. Let's see. All right, there's one last piece of information that I want to probably convey with you, but I'm not going to teach you this full on. Let's just get to this on Wednesday. It's a different way of writing things, and it's kind of advanced. What do you want to do with physics? Do you want to actually be an engineer or a physicist or what?
Like I said, as long as I can with it.
Then probably engineer.
I'll do it.
Then probably engineer. So what I'm going to show you right now is kind of an engineering notation. What I mean by the word notation is, do you know what I mean by notation? It's a way of the way engineers write things down.
Not quite.
It's the way they write things down to organize thoughts in their head. Okay. What I'm going to do is I'm going to show you a way of writing something down, so that way you can, like if you see it done in engineering books, it won't freak you out. Okay.
Okay.
There's the coordinates x, y, and z. Cool? And this is a three-dimensional coordinates.
Cool.
Usually we have this x and y, but I can also draw my z direction as z, which comes out of the board. We cool with that? Yes, no?
Right.
All right. So what I'm thinking is, if I have a force, now let's get rid of the z component just because that's always confusing and I'm not going to really worry about that for now. Let's just deal with x and y's. To be honest with you, you want to know how hard doing things in 3 dimensions is?
3 times as hard as 1-dimensional physics?
Yeah. It's no harder than 2-dimensional physics. It's just one more extra step. So, in fact, it's so easy that I don't think I ever show you how to do 3 dimensions. I just kind of assume that you know how to, do it.
Yeah.
In fact, this notation that I'm going to introduce to you makes it easy to do 3-dimensional physics. So, say that I have some force that acts at an angle theta. Are we cool? Now, in the past, what I've done is I said, all right, then there's an fx and an fy. Can you tell me, just by looking at this triangle, what fx is?
Fx would be fx times sine theta.
No, it's just f cosine theta.
Right.
And this one's f sine theta. Cool?
Oh, right. Sorry, I got that mixed up. Yeah.
Now, one way to write this is instead of writing 2 separate equations, we just write f all together. And we put a little arrow on top to indicate that this is a vector we're talking about. Okay?
Okay.
Now, this vector has 2 parts to it. It has an x part and a y part. Actually, I'm going to make it like this.
Right.
It has an x part and a y part. Are we cool? What is the x part?
Mm-hmm.
The x part is f cosine theta. What's the y part?
Right. F sine theta.
F sine theta. And these little hats, in fact, that's literally what we call them, x hat and y hat. That's to indicate that this is the x component. Here's the force, and this force is made up of this amount of force going in the x direction and this amount of force going in the y direction. This is no new physics here at all. I'm just showing you a different way to write these. This is the same as this. And a lot of times, engineers like to use this, because in one line, they can put all the different pieces of information they need. You see that? So this is the x hat and the y hat. The hat means the x direction and the y direction. So this is the amount of force. Here's the magnitude. Remember, a vector has a magnitude and a direction. So here's the magnitude, and here's the direction. Here's the magnitude, and here's the direction.
Oh, sweet.
Are we cool?
Yeah.
That's a different way of writing it. Some physicists, a lot of times physicists don't use this specific notation. All they do is they change this to an I and a J. The reason being is because, I don't know, for some reason we just want to be smug or something like that, and then we say, well, I'm not going to call it XYZ, I'm going to call it I, J, K direction. You'll see that a lot in advanced chemistry or physics books. It's really the same thing. Don't get too freaked out if you see an IJK instead of an XYZ. It's really the same thing. Engineers, on the other hand, they like using X and Y and Z. Yeah. And it's a different notation. And it's really helpful notation, though. We cool? So let me give you an example of how we would do something like this. Like, let's say my force 1 is equal to 3x hat plus 4y hat. And my F2, I have two forces, and this one's equal to negative 5x hat plus 7y hat. Excuse me. What is F1 plus F2?
That would just be...
It's negative 2x hat plus 11y hat. It's very simple.
Oh, is that really it?
You add the x with the x and the y with the y. Because remember, back when we were doing this stuff separately, we added up all the forces in the x direction. That would be only looking at the x hat direction, add up all the forces. Right? We did this sum of the forces in the x direction. And then separately, we did sum of the forces in the y direction. This is doing both of those steps simultaneously. It's saying, let's look at the x hat direction, and let's only add the stuff in the x hat direction. So that would be the 3 and the negative 5, negative 2. Now let's look in the y hat direction, and we'll only add things in the y direction. 4 and the 7. 4 plus 7 is 11. Done.
Huh.
Do you see how this notation can be quite advantageous?
Mm-hmm.
All right. That's it. That was some advanced stuff. It really wasn't that hard, I don't think. But
no,
you might see that.
Because I believe you went over this.
You might see it. And if you see it, don't freak out. It's not bad.
Okay.
Okay? All right. Talk to you later.
Cool. See you, Mr. Dalday.
See you.